For inference with generalized linear models, you already covered the use of a walled test to test the significance of a single regression parameter, and you covered the deviance test statistic to compare nested models in the Poisson regression model setting. Now you will go beyond this setting and also cover the use of drop-in deviance tests with more general GLMs. So here are the preliminaries. In a generalized linear model, the response or outcome, yi, of policyholder I, will be estimated or predicted with an estimate for its expected value. That is mu hat for observation I in this case. Now consider two extreme positions. On the one hand, in the so-called null model, each response gets the same estimate or prediction. That's the global average, here denoted with y bar. And this is, of course, an overlying simple model, which only uses one parameter and is therefore too simple to model or to explain your data. On the other hand, in the saturated or full model, each response is estimated by its actual value. So in a sample of size n, this approach would estimate n parameters. So the model replicates the data instead of explaining them. The model clearly overfits the data and picks up not only the trend, but also the noise in the dataset. Well, the so-called deviance statistic is then a likelihood ratio test statistic that balances the regression model under consideration against the full or the saturated model. And to see its general specification, let us start again from the log likelihood of a generalized linear model in the general notation developed in this deck of sheets. Using the relation between the parameter theta and the mean mu I of response or observation I in the GLM framework, you will replace the theta I with B prime inverse evaluated in mu I. This substitution allows you to write down the log likelihood of the GLM in terms of its mean parameter, the mu I. This is the so-called mean parameterization of your generalized linear model. Now, for a specific regression model under consideration, write the corresponding log likelihood as L evaluated in mu hat. And you want to compare this attained log likelihood for the model under investigation against the log likelihood of a full model, where each observation is replicated. Thus, the mu hat equals the y, the observation itself for observation I. Now, the likelihood ratio test statistic of interest compares the log likelihood of the regression model under consideration against the log likelihood of the full model. That's the maximum value of the likelihood that can be achieved with a model that is overfitting your data. You can see here at the top of the sheet how this likelihood ratio test statistic can be written. So note that we write down this statistic as a random variable, and for that reason we're using the random variable, so the capital Y, to denote the responses as random variables. So what you do here is you take -2 times the logarithm of the likelihood of the model under investigation divided by the likelihood of the saturated model. And that's in fact what you see here with the difference in blue and in red. Now for the function a of the dispersion parameter phi, we often use the following expression. So that's phi divided by an observation-specific weight w. So the expression derived as such is the so-called scaled deviance statistic. It is the deviance divided by the dispersion parameter phi. That's what you get here if you construct this likelihood ratio test statistic that compares the model under investigation against the full model. So do note that in the setting of Poisson regression, the expressions for deviance and scaled deviance are the same, they're equal, because the dispersion parameter in our Poisson regression example would be fixed, it would be equal to 1. However, as you can see here, in a general setting, the dispersion parameter is unknown, and therefore it has to be estimated, and the scale deviance reflects this. Now, before moving on with discussing other useful statistics and inferential tools based on these, you will derive here the deviance and the scaled deviance test statistics for one particular example of a generalized linear model, in casu the normal linear regression model. So the log likelihood as a function of the mean mu I of observation I and variance parameter sigma squared is printed top of the sheet. Now recall that mu I, the mean of observation I, is expressed as a vector xi transpose times a vector beta with the regression parameters. Thus, this GLM uses the identity link function, and the dispersion parameter here equals the variance parameter sigma squared. That's what we also derived earlier on in the course. The scaled deviance statistic then becomes the sum of the squared differences between the response variable y and the estimated mean, the mu hat I. And we scale that with the dispersion parameter sigma squared. If useful, a weight wi could also be included in this expression. So this is what you get. It's the sum of squares, or the sum of squared residuals, divided by sigma squared. That's what you get here for the scaled deviance test statistic if you work out this formula. Now, the deviance test statistic in this example then simply corresponds with the well-known sum of squares. So it's the sum of the squared residuals, or the sum of the squared differences between the responses and the fitted values. Again, an observation-specific weight wi could be included here, which would then lead to a so-called weighted sum of squares. So to conclude this example, if we write down scaled deviance and deviance test statistic for the normal linear regression setting, we get something very familiar, and we recognize here the residual sum of squares. Now, next to the deviance and the scaled deviance test statistic, another useful statistic for inference in the GLM setting is the Pearson statistic, denoted here with chi-square. And this statistic is defined as the sum of the squared differences between the response variable yi and its mean, as estimated by the regression model under consideration. So we take that squared difference and we divide by the variance function evaluated in mu hat I. And recall that earlier in this course we specified this variance function v evaluated in mu hat y as it's the part of the variance that expresses, that captures how the variance is changing with the mean, how the variance depends on the mean. So that's what you see appearing over here. Now, putting this to practice, let's consider once again the example of the normal linear regression setting. The variance in this particular regression model does not depend on the mean. It's a fixed variance. Indeed, this type of regression implies the assumption of homoscedastic errors and therefore constant variance, denoted here with sigma squared. The Pearson statistic reduces then to the sum of squared residuals and thus equals the expression that we just derived for the deviance test statistic. In the case of normal linear regression, both the Pearson statistic and your deviance statistic coincide. Right, so it turns out that asymptotically, one can rely on interesting distributional results for both the deviance and the Pearson statistic. These distributional results are relevant to derive inferential tools for GLMs later on in this video. For the normal linear regression, you may recall the distribution of the sum of squared residuals. And this sum of squares is distributed as sigma squared, the variance, times a chi-square distribution with n minus p plus 1 degrees of freedom. And here n is the number of observations in the sample, and p plus 1 is the number of regression parameters which are estimated. So that's an intercept plus p regression parameters to capture the effect of covariance in a linear predictor. This result generalizes in the GLM setting as follows. So that is, both the deviance as well as the Pearson statistic have an asymptotic distribution that equals the dispersion parameter, phi of the GLM, times a chi-square distribution with degrees of freedom n minus p plus 1. So that's a useful result. Now you're now ready to derive the so-called drop-in deviance test as a formal tool for inference with generalized linear models. And this test will compare nested models, where the model in the null hypothesis is a simplification of the model in the alternative hypothesis, which you obtain by putting Q regression parameters equal to 0. And the drop in deviance test statistic is then defined as follows. So it is the difference, and therefore the drop, between the scale deviance from the reduced model, so that's the model under the null hypothesis, the difference between the scale deviance from the reduced model and the scale deviance from the larger model, the model that you get in the alternative hypothesis. You can also see this as the difference between the sum of squared residuals from the reduced model under the null and the sum of squared residuals from the bigger model under the alternative hypothesis, appropriately scaled. So the last bullet here reveals, in fact, an interesting similarity with the extra sum of squares f-test that we know from normal linear regression. However, in the GLM context, a new type of residual is used, in this case, the deviance residual. The deviance of a regression model under investigation equals the sum of its squared deviance residuals. And that's where this definition of the deviance residual is coming from. More on this later in the video. Well, you will now develop the drop-in deviance test statistic as an example of a likelihood ratio test statistic. So denote with LH0 the log likelihood as maximized under the null hypothesis, and let LH1 be the log likelihood as obtained under the alternative. The likelihood ratio test statistic, which compares the likelihood under the null hypothesis and the likelihood under the alternative, can then be written as you see here on the sheet. And in this notation, we use S and LS to refer to the saturated or full model and its corresponding log likelihood. So what you recognize here is the scale deviance of the model under the null hypothesis minus the scale deviance of the model under the alternative hypothesis. And that's why we refer to this test statistic as a drop in deviance test statistic. So the drop in deviance, that's the test statistic that will be used to decide whether you will continue with the reduced model from the null or with the larger model from the alternative hypothesis. And how are you going to take this decision? Well, intuitively, a small realized value of the drop in deviance test statistic suggests that the likelihoods realized under the null as well as under the alternative are approximately equal. And that implies that the reduced model, specified in the null hypothesis, does explain the data about as good as the larger model from the alternative does, right? But a realized value of this drop in deviance that is large would imply that the likelihood as maximized under the null is way larger than the likelihood that is realized under the alternative hypothesis. Thus, the reduced model is inadequate in explaining the data. So you will formally evaluate whether the observed drop in deviance is small or large by comparing its value with a quantile from a chi-square distribution with q degrees of freedom. Note that this result only holds when the dispersion parameter phi is known, and it does not require estimation. This is the case, for instance, with a Poisson regression, where this phi would be equal to 1. But what would you do in case the dispersion parameter phi is unknown? Then you will have to estimate it. And a possible estimator is the following. So use the deviance statistic obtained with the larger model under the alternative hypothesis and scale it by dividing by its degrees of freedom. In a model with p regression parameters and an intercept and a sample of size n, this degrees of freedom would be equal to n minus p plus 1. But when phi needs to be estimated, you will work with the following test statistic. You will take the ratio of, on the one hand, the drop in deviance divided by q, and on the other hand, the estimator for the dispersion parameter phi. And note that the q here is the difference in the number of parameters between the regression model under the alternative and the regression model under the null hypothesis. So it's typically, it is the number of parameters that you put equal to 0 in your null hypothesis. Now, to decide whether the null hypothesis should be rejected or not, you will compare the observed value of this f-test statistic with an f-distribution with q and n minus p plus 1 degrees of freedom. That is, if the observed value of your statistic is larger than a high quantile from the f-distribution, then the null hypothesis cannot be accepted. The parameters considered in the null hypothesis should not be put to 0, and the larger model is to be preferred. Do note the analogy between this test and the partial f-test, which we know from normal linear regression models. Now, a final item that we wish to cover in our discussion of GLMs is the notion of types of residuals, specifically defined for generalized linear models. So recall that in regression models, residuals are typically explored to assess the adequacy of the fit of a model in terms of, is the variance assumption adequate? Is the link function that is used, is that a suitable choice? Is that a good fitting choice? Are the covariates included in the linear predictor? Are they included there in an appropriate way, or do we need to take a transformation of a certain covariate before plugging it in the linear predictor, and so on? Moreover, the inspection of residuals may also reveal the presence of unusual observations. So it is clear that residuals matter in regression models, but for GLMs, an extended definition of residuals is required, one that is applicable to all distributions from the exponential family. And a first type of residuals used in this context is the so-called Pearson residual. And these residuals use the difference between the response and fitted value, the mu hat, but scale it with the square root of the variance function evaluated in this fitted value. As such, the raw residuals are appropriately scaled. And a particular feature of those Pearson residuals is that if you take the sum of the squared Pearson residuals, you get the Pearson statistic as defined earlier on in this video. And a similar observation holds for the deviance residuals. So the deviance residuals, they are defined in such a way that the sum of the squared deviance residuals equals the deviance of the model under investigation. So that's how you should picture those deviance residuals. A detailed derivation of the expression for the deviance residuals in the case of Poisson regression is given on this sheet, and this relies on the expressions derived earlier on in this video. Both Pearson as well as deviance residuals can be extracted easily in R software after calibrating a GLM. So that concludes the video. We covered some inferential tools for decision making with generalized linear models. We discussed different types of residuals which do matter in the framework of generalized linear models. And we will continue now with a demonstration of fitting a generalized linear model with R.